Right, ladies and gents, carrying on from where we left off last time, we're going to take a look today at series harmonic resonance, and most importantly at its implications for circuit. Okay, so if we take a series circuit with at least one R, one L and one C component in, as shown there, and we apply an AC voltage, series resonance will occur when omega L is equal to 1 over omega C, i.e. at the point where both the reactances XL and XC are opposite in direction but they're equal in magnitude. Yep. So the ohm value of them is exactly the same. When that happens, they cancel each other out in the impedance formula. If those two are equal, that bit must be equal to 0, and so the overall impedance at series resonance is just the resistance of the circuit. And if you think about it, if any of these if we change the frequency, if we put the frequency up, this line will get longer, that one will get shorter, the overall reactance will be the difference between the two, and the impedance line must lengthen. So that at series resonance, the impedance is as low as that's ever going to be because it's just the resistance. At any other frequency, the overall impedance magnitude is going to increase, and we're going to get an angle as well as that changes. Going the opposite way with frequency would see XC increase and XL reduce, and therefore it'll bring the phasor down this way, but the same effect on the overall magnitude of the impedance must get higher. Yep, okay. So, this, if it's filters, tuning circuits where resonance is to good effect. But if we have unintentional frequencies, it has the potential problem that happen in higher power, higher voltage circuits with the active. For an example, involved. So we've got a circuit there, 2 ohm resistance, 500 millihenry inductor, and 0.2 microfarad capacitor. We're going to apply a voltage there, so 600 volts at where there's 335 pi, and 20 volts where omega is 1005. So a third harmonic. So it's harmonic in that. And the going to and the harmonic, the third harmonic, is unwanted, undistortion. Okay? So when there's a note there, when you get to calculating the voltages, the angles for the purpose of this can be ignored because the magnitudes of the voltages and currents that we're interested in. Okay, start with this circuit at the fundamental frequency. That's at omega equals 335 pi. So I'm going to call it Z1 for meaning the impedance at the fundamental. Yep. R plus omega L right XL. Okay, so in order to do that, what we got to do? So we better call them XL1 and XC1 as well, haven't we? XL1 is equal to and that equals 526.2 units. Yep, I'll give you the frequency in omega. Omega's 2 pi f. Yeah. Okay. So you can get XL from 2 pi FL or omega L. Yep. Okay. Because omega is 2 pi f. XC1 1 over 335 pi times capacitance 0.2 times 10 to the minus 6 farads. Yeah, so we got an XL at fundamental of 526.2 and a XC1 of 4751 ohms. So the capacitive reactance at this frequency is much bigger than the inductive reactance. Yeah. So now we can go and calculate Z1 as being the resistance 2 ohms plus 526.2 minus 4751 J, and we want to convert that to polar. Yeah, so having done a bit of calculation, we determined that the overall impedance of the circuit at the fundamental frequency is 4,225 ohms at an angle of minus 1.57 radians. That's what we would expect. We got a lot more capacitive reactance than we have either resistance or inductive reactance. So we're going to expect a steep angle on the impedance. Yeah. So from that, how can we calculate the current? I at the fundamental. Yeah, 600 divided by this 4225 angle minus 1.57. So 142 milliamps would flow, that 600 volts applied. And we're assuming that that's the design current, that's the intended input voltage. There's a perfect sine wave where omega is 335 pi. Yeah? Okay. Now, how do I find VL? 1. Yeah. I times XL, which is this 0.142, angle 1.57. Multiply that by 600, angle nothing, equals. We're not really overly interested in the angle, but no, hang on, XL, sorry. My XL was 526.2. Angle, not in degrees. Pi over 2. Like I said, we aren't overly concerned about the angle. What we're interested in main is the magnitude of the voltage to compare to that we get for the third harmonic. .3 then, yeah. .7. Yep. And VC1 and that was 4751. We got there, Jack? So 675 volts then, yeah? Angle 0. Cancel each other out. Yep. So that capacitor voltage is a little bit higher than the intended applied, but if we had, let's say, I don't know, 1000 volt working capacitor, then everything would be okay. Yep. For instance. So 600 volts applied, we got 142 milliamps flowing, we've got 75-ish volts across the inductor and 675 volts or so across the capacitor. And we assume that that is what was intended. Okay, so moving on to the next page, We'll calculate the current and inductor capacitor voltages at the third harmonic frequency. First, determine the circuit is resonant at omega 3 equals 1005 ohms. So what we're going to do to determine that? What do we know about resonance? Find out XL3, find out XC3, and see whether they're near as damn it the same. So how do I calculate XL3? There's omega 3 times L, which is 1005 pi times 0.5 equals nope. Oh yeah, just give me a ohmic value for that. Normally I would advocate leaving it as a number times pi, but in this case I want to see how close the actual two values are to each other. XC3 is 1 over omega 3 times C. That's 1 over 1005 pi times 0.2 and 10 to the minus 6. Anyone got a result for that for me? No, it's not that. You hadn't done the 1 over, I reckon. 1584. Okay, so those two are near as damn it the same. We can say that round for rounding errors, or minor errors, XL3 not equivalent to, approximately equal to, and therefore resonance occurs. Third harmonic, therefore Z3 is equal to R is equal to 2 ohms. Angle for a resistor, who's considering it? Nothing. Sorry? No. No. You're matching the input and output port. Anyway, filter network. It's not what. Okay, so we can say, we can assume that we can throw away any extra and say the impedance now is which is 2 ohms. Right, so the current I at the third harmonic is equal to the third harmonic voltage divided by R. Third harmonic voltage in this case is 20 volts divided by 2 ohms equals 10 amps. So what we had 142 amps do to that 600 volts of fundamental, we've got 10 amps, 20 volts of harmonic distortion. We'll talk about that in a minute, what the implications of that are. Yep. And if XL is equal to XC, then VXL is equal to VXC, and that's equal to I times either of the two. Will take XL 10 times X pos or one's got a voltage of 15,790 with a positive 90-degree angle. Doing that, we're not going to play the so what was it? Well, yeah. In a tech way, yes, they do. Be more specific. Be more specific, Alex. If we assume that the circuit's designed so that it has 142 milliamps current flowing, so you'd allow for a cable that will take an amp, probably, yeah, maybe 2 or 3 amps. Yeah, your highest voltage across components at the fundamental frequency is 675 volts. So you'll install a capacitor with a working voltage, let's say about 1000 volts, and everything will be okay. Yeah. You'd have insulation on your inductor that would withstand 1000 volts, maybe a little bit more. You'd allow a margin for error. But would you allow so what would about such a situation, what would you do in terms of a circuit so that that situation didn't go on for too long? Yeah, you'd incorporate some protection. Yeah. So at best, that's the best that would happen. Circuit breaker tripping because of the high current. And what were we saying? How many times increase? 7. If protect, yeah. If not properly protected, one. Capacitor destroyed by overvoltage. If that's a paper one wrapped in a can, the can will burst and you'll have paper everywhere at best. If you're standing near it, you'll not enjoy very much. There's a big. Yeah. So capacitor destroyed by overvoltage, it will. One thing blow. 2. High current, higher than expected. Including on cables. That feed it. 2. And I'm not sure you'd. Not an expert on these regulations. What's about the circuit is there's no fault with the circuit that's been But because of this unwanted harmonic in the trip and 8, but can't too easy, simple in electric. Why? What I've set up for you after that is try this one. This is based, do you remember the big iron core in? Determined what the inductance was at different positions. This one's based upon one of those inductors. So they have a maximum current rating of 2 amps. Tino the way in is around about 670 millihenry. One of them, I don't know. It's got some. Connect. That has a working voltage of 5 volts. So we're making some assumptions. I don't know if they're connected to the capacitor of a suitable value. Well, but not apply 60 volts at the third harmonic, i.e. 60 volts at 150 hertz equal to 3. The calculations to what you determine prove that it's not a good idea. Okay, it's not a good idea to put 150 hertz at 60 volts on that inductor. All right.